Hi, I'm Josh Lovell, Product Line Manager for Teledyne ISCO's Pharmaceutical R&D products. Thanks for joining our regular chromatography webinar series. Today's topic is focused on choosing whether HPLC or SFC is more suitable for your separation. As a reminder, if you have any audio-video issues, please exit the webinar and rejoin. This usually resolves the issue. If you have any questions during the webinar, please utilize the Q&A feature within Zoom. All questions will be answered at the end of the webinar. The webinar will be recorded and made available for future viewing. Today, we are excited to introduce one of our Teledyne ISCO in-house application specialists, Dylan Cavey. Dylan is one of several application chemists that we have at Teledyne ISCO to help customers determine the best route to a successful separation. For any of your tough separation questions, please reach out to any of our experts with your questions. At this point, it's my pleasure to hand it over to Dylan.
Hey, thanks everyone for joining today's webinar. As previously mentioned, I'm Dylan Cavey. I'm an applications chemist here at Teledyne ISCO, and today I'm going to try to help you guys decide when to use HPLC or SFC. And a lot of that's going to come down to the analytical needs of your laboratory and what compounds you're looking to separate and purify. Are you looking at chiral compounds? Well, then you might look at using SFC. If you're looking at aqueous samples, you might choose HPLC. So we're going to dive into the pros and cons of each of these chromatography techniques and when you might want to use one over the other. To start today, we're going to talk about SFC. And if you're not familiar with supercritical fluid chromatography, this will be a good background section to answer that question. We're going to dive into what a supercritical fluid is, and we're also going to dive into supercritical fluid mixtures, because a lot of the time in SFC, you're going to have to add a modifier to your supercritical CO2 to try to increase the polarity of your solvent system, which will then allow you to elute more polar compounds off of your column. Then we're going to compare HPLC and SFC with a tail of the tape. So we're going to look at the solvent usage, how much time each of these chromatography techniques are going to take, and we're going to even look at energy consumption. Just a good way to look at the pros and cons of these two different chromatography systems. Then we'll look into a comparison study. We looked at a chiral separation and we used HPLC and SFC to distinguish between the two enantiomers with this chiral separation. So we're going to compare HPLC and SFC there as well. We're going to also look at stacked injections and what does that mean for your laboratory? How much solvent, how much time will stacked injections save you? And then we're going to dive into where you might want to choose HPLC over SFC. A large portion of this webinar, especially early on, is going to be very favorable to SFC. There's a lot of pros that the supercritical fluid allows a user to take advantage of with SFC. So at the end, we're going to go over some different areas where HPLC might be used over SFC. So we're going to talk about some aqueous samples, also look at some close eluting achiral separations.
So what is supercritical fluid chromatography?
First, we have to answer the question of what is a supercritical fluid. And to help with that, we're going to look at the phase diagram on the left. And you can see that we have pressure on the y-axis, temperature on the x-axis, and we have these black lines throughout the phase diagram that indicate phase changes. So let's say we want to do vaporization and go from a liquid to a gas. Well, we'd have to cross one of these boundaries and perform a phase change in order to do so. Same could be said for melting, going from a solid to a liquid, or sublimation, going from a solid to a gas. We're going to have to perform a phase change and cross one of those boundaries. But if we look at supercritical fluid, you can see that those black lines aren't there, and that's because there is no definitive phase change when going from a liquid and a gas to a supercritical fluid. Now, a supercritical fluid is going to act as both a liquid and a gas. It's going to have some characteristics of a liquid, and it's going to have some characteristics of a gas. And we're going to get to those characteristics a little bit later when we're looking at the tail of the tape comparing SFC and HPLC. Now, the other thing I will highlight in this phase diagram is the critical point. Now, anything above the critical point in terms of pressure and temperature is going to result in your supercritical fluid. You can also see on the Y and the X axis that the critical pressure and the critical temperature are highlighted. This chart on the right is also going to highlight those different critical temperatures and pressures for a couple different compounds. And with these different compounds, most of the time it's either going to have a really high critical temperature or it's going to have a really high critical pressure. The one that's going to be used the most in SFC is going to be your supercritical CO2. You can see it has a really achievable critical temperature and a really achievable critical pressure. The one that's closest to carbon dioxide is right below it. It's nitrous oxide. Nitrous oxide is also referred to as laughing gas. As you can imagine, that is probably why we don't see too many SFC systems using supercritical nitrous oxide. I really don't think that's going to increase productivity. It's safer to stay with your supercritical CO2. Now, majority of the time we're going to have to add a modifier or a co-solvent to our supercritical CO2 to try to increase the polarity of our solvent system. As you guys can imagine, CO2 is extremely non-polar, and in order to elute polar compounds off of our stationary phase, we have to find a way to increase the polarity of that solvent system. And the way we're going to do that is with a co-solvent or a modifier. So if we look at this diagram, on the left, you can see the z-axis is the composition or the %B or % co-solvent within that supercritical CO2. So if we're at 0% co-solvent, that means we have 100% supercritical CO2, which is indicated by that boiling line for pure A. And there's a dot that connects to this dotted line, and that's going to be our critical point for carbon dioxide. And the same can be said for 100% co-solvent, which in this case is methanol. You can see the critical point for methanol there as well. So anything above that critical point for pure A is going to result into a supercritical CO2. Now the same could be said for 100% methanol. Anything above that critical point will also result in supercritical methanol. So there's going to be a line that connects these two, that dotted line that indicates the critical point for any %B in between. The diagram on the right is another way to look at this, and you can see that this shaded region is actually where we're going to be in both a liquid and a vapor state. So this is a two-phase region within this diagram here, and you can also see that this diagram is also cut at the 25 degrees Celsius mark just to show that isotherm at 25 degrees Celsius. So anything below or within this shaded region, which has each critical point going from 100% to 0% B within it, anything above that is where we're going to be one phase. This is going to be the supercritical region. Now that we have a background of what SFC is, let's talk about how HPLC and SFC differ. Let's now take a look at the tail of the tape between SFC and HPLC. And what's going to be the main difference between these two chromatography techniques? Well, that's going to be the mobile phase. We just spent a lot of time talking about SFC and how it uses supercritical fluid as its mobile phase. Well, HPLC is going to use a pressurized liquid, and that's actually going to allow SFC to run 3 to 4 times faster in terms of its linear velocity. And a lot of those reasons are due to these next 3 points: its diffusivity, its density, and its viscosity. Supercritical fluid is going to have a higher diffusivity, it's going to have a lower density, and it's going to have a lower viscosity compared to HPLC. And that's going to allow it to have shorter runtimes. So you can achieve close to 3 times shorter runtimes with SFC than you would with HPLC. Another thing to think about is you're going to have a lot less organic waste. Since we're using supercritical CO2 as one of our solvents, that's going to really cut down on the amount of organic waste you're using with SFC. Another thing to keep in mind too is your energy consumption, and that can be almost 7 times lower with SFC compared to HPLC. Now, if we look at this tail of the tape, it looks like it's a runaway for SFC, but there are still times where HPLC might actually have more pros than SFC. One of those pros could be the fact that you can use reverse phase in HPLC, and this is also going to open up the door to a lot of other stationary phases that you could use with HPLC when compared to SFC. And a lot of people are starting to dip their toe into SFC, but their bread and butter is going to be HPLC. It's tried and true. People are more familiar with it and people are more comfortable with it. And you can also change all of your solvents with HPLC. With SFC, you're always going to have to use supercritical CO2. With HPLC, you have all your solvents at your disposal. Let's take a look at a Van Dieter plot comparing SFC and HPLC, and this is just going to highlight some of the characteristics we just covered with the tail of the tape. You can see on the y-axis we have our height equivalent to a theoretical plate, and a theoretical plate is just the minimal distance solvent has to travel for an absorption and desorption state. And I like to think about this in terms of a staircase. Let's say you have a staircase that has a really high step that you actually have to reach up and pull yourself above in order to reach that next step. Well, you're going to exert a lot of energy and you're not going to be very efficient going up that staircase. But let's say you have a staircase that has very small steps, one that you barely have to lift your foot up to reach the next step. Well, then you're going to be very efficient going up that staircase. And the same could be said with theoretical plates. The smaller these theoretical plates, the more efficient your column is going to be. On your x-axis, you're going to have linear velocity, and that is not flow rate. This is the speed at which the solvent is going to travel. This solvent font is going to travel through the column. So this is a distance over time measurement. In this diagram here, we're using centimeters per second. So let's look at an HPLC system with a height equivalent to a theoretical plate at 0.0125. You can see there our linear velocity, we're going to be less than 0.2 centimeters per second. But if we are using SFC, because we're using that supercritical fluid as our solvent, you can see how much faster we're able to run and complete this run due to this increase in linear velocity. The tail of the tape, we talked about how much solvent and time SFC can save you compared to SFC. So now let's actually put that to the test with a solvent and time comparison study. Our solvent and time comparison study, we're going to look at a chiral separation. And a chiral compound cannot be superimposed on itself. So if we have this original compound on the left and we have its mirror image on the right, no matter what we do to that compound on the right, no matter how we twist it and turn it, there's no way we're going to be able to make it look exactly like that original compound. You can see it here. This is the close we can get. We have the purple and the blue group exactly like the original compound, but we have the black group pointed forward and the red group pointed behind, which is the exact opposite of the original compound, which had the red in front and the black behind. So that's what a chiral compound is. And actually SFC has become the preferred technique for these chiral separations due to its increased diffusivity, which leads to improved fractionation purity. It also has decreased method development time, and it also has a lower pressure drop, which allows for column coupling. So you can run an achiral separation, then go directly into a chiral separation, or vice versa. It really allows labs to be more efficient with their time. So for this study, we're going to look at these trials still being oxide and enantiomers. So we have the R and the S version, and we'll see those get separated with the SFC and HPLC.
Here's our SFC pilot injection using a ES Industries chiral CCS column. We only loaded 0.5 ml of our TSO sample onto that column. We also ran it isocratically at 10% methanol in our supercritical CO2. If we look at the separation, you can see that we're getting almost down to baseline resolution between the two enantiomers. The runtime was approximately 3 minutes, and the amount of waste we produced was 77.5 mils of the methanol. Again, that CO2, that supercritical CO2, is not adding to the waste, as that is going to be exhausted through the system. We used flow rate of 80 mils a minute, and our oven temperature was at 40 degrees Celsius. The back pressure regulator was set at 100 bar. And again, if we look at that resolution, we're almost getting down to baseline resolution. Now here is our HPLC pilot injection, still using that same ES Industries column. We're only loading 0.5 ml of our TSO sample. And if we look at the resolution with this HPLC system, with that ES Industries column, it's pretty similar to what we saw with the SFC. We're still able to separate those two enantiomers, almost getting down to baseline resolution. Now, the big difference between the HPLC and the SFC is going to be that runtime. Due to that supercritical fluid, SFC is able to have 3 times shorter runtimes. Well, we see that here with this pilot injection for the HPLC taking approximately 11 minutes, which is significantly higher than what we saw with the SFC. Now, the other thing we had to do with the HPLC is try to mimic the solvent system we saw with the SFC. The SFC is going to use that very non-polar supercritical CO2 with a polar co-solvent, which was methanol. So in order to mimic that, we used hexane, which is also very non-polar, and then used IPA in hexane. So we used 10% IPA in hexane. We had to use IPA in place of methanol just because IPA is miscible with hexane. So it used a total of 240 mils of solvent, and that's including the wash and the equilibration. All of that was sent to waste, which is quite a bit higher than what we saw with the SFC system, which was close to 80 mils of solvent being sent to waste because of that supercritical CO2 just being sent to the exhaust that was not collected in waste. So that supercritical CO2 saving you on your organic solvents there. The other thing that's different between these two pilot injection is we were only able to get to 18.9 mils a minute in terms of flow rate with the HPLC system, which is significantly lower than the 80 mils a minute we were able to run on the SFC system. But again, if we look at the resolution, we're seeing similar resolution and separation between these two TSO enantiomers. But when we compare them head to head, what do we see? Well, we actually get a savings of 162 mils of solvent when we run this injection on the SFC, and we save close to 8 minutes of time when we run this separation on the SFC. Now, the other thing we're able to do on the SFC is stacked injections. So what are stacked injections? Well, stacked injections are exactly what they sound like. We're going to add a little bit of our sample during a cycle time. So if we look at this chromatogram on the screen now, that we have these blue dotted lines throughout the chromatogram. So that's where we're going to make an injection. And this run is an isocratic run. You can only run isocratic runs with stacked injections because you're going to continually add sample onto the column from the loop during these designated cycle times. So you can see this cycle time is about 1 minute. So every minute we're going to add another 0.25 mils of this TSO sample onto the column. And since we're running it isocratically, those slugs on the column of that TSO sample are going to just continue to trickle down the column at the same rate. So that allows us to perform these stacked injections where we're able to complete a number of injections, a number of separations in a limited amount of time. So here we did 10 injections, 10 stacked injections, and on the SFC that only took us 9 minutes, and we only produced about 120 milliliters of waste from the methanol or co-solvent, and that's including both the wash and the equilibration. stage. Now we kept the flow rate the same at 80 mils a minute, kept the oven temperature at 40 degrees Celsius, and the back pressure regulator was still set at 100 bar. But you can see we're still seeing that same resolution, that same separation between these two TSO enantiomers throughout all 10 injections. We're also able to pool our fractions, so that first enantiomer is always going into tube number 1, that second enantiomer is always going into our second test tube. And we're seeing pretty good separation throughout all 10 injections, and this really cuts down on our amount of runtime. Now, currently on the HPLC, we can't run stacked injections, but you can set up a queue to perform 10 different injections. So that's what we did here. We used the queue to add 10 injections back to back to back in order to complete or compare the HPLC to the SFC. So we ran these 10 different injections in the queue, and you can see that the total time it took to complete those 10 injections was 126 minutes. And a large part of that is because with each of these injections, you have to go through the equilibration stage for every single run you do, and it has to perform a wash after every single one of those injections. So again, we were looking at a hexane IPA solvent system, and that produced close to 2 liters of waste. So that is significantly larger than what we saw with these stacked injections from the SFC. The flow rate remained the same as we saw with the HPLC pilot injection, but you can see here, this is really where the SFC is able to increase your solvent savings and your time savings. So when we stack these Q injections to the stacked injections, what do we see? Well, we actually see a saving of almost 1,800 mils of solvent and close to 2 hours of work time when working with these stacked injections compared to these 10 queued injections from the HPLC. Now, theoretically, we should be able to run stacked injections on the HPLC as long as we keep that run isochronically like we saw with the SFC. So if we keep our runs at 10% IPA and hexane throughout the whole entire run, we should be able to perform stacked injections. So theoretically, we went through that and we calculated the amount of runtime and the amount of solvent you would have to use to perform 10 stacked injections on the HPLC system. And when we did those calculations, we have a runtime of close to 22 minutes, and we're still producing over half a liter of solvent, and we kept that flow rate at 18.9 mils a minute. So when you stack this theoretical stacked injections on the HPLC, compare that to the stacked injections on the SFC, what do we see there? Well, the SFC is still going to save you about half a liter of solvent, and you're still going to save 13 minutes of work time. And this just highlights the ability of that supercritical CO2 and what that does to increase your efficiency, increase your work time, and increase your solvent savings.
So thus far, we've really highlighted the pros of the SFC in terms of its supercritical fluid, the speed it's able to run at, the solvent saving capability, the time saving capabilities of SFC. So when might you use HPLC over SFC?
So here's a chart that if you've ever Googled SFC versus HPLC will pop up, and it shows you what stages of SFC can separate what compound. So if you're looking at separating pentane, well, if you look at that green bar there, you could just use pure CO2 to separate that. And if we look at the lower half of this chart, that's our HPLC. So if we want to look at separating some alcohols, well, we could either use normal phase HPLC or reverse phase HPLC. And if we wanted to use SFC, we'd have to use our supercritical CO2 or and a modifier, and that's our addition of our co-solvent. And you can see that eventually the farther we go in polarity with those compounds that we want to separate, eventually those green bars stop at that inorganic ions, large proteins, DNA, RNA, where if we look at HPLC, they continue with that ion chromatography, that ion exchange. But Really, the polarity limits of SFC are still to be defined. The latest thing in SFC is to use supercritical CO2. You're going to use your co-solvent, but now people are starting to look at adding water to that solvent system, and water is really going to increase the polarity of that SFC solvent system to try to elute some of these high polarity compounds. But this is also an area where HPLC might be a better choice. So what we're going to look at first is using aqueous samples. And can we get these highly polar aqueous samples off the column with SFC, or do we have better luck with the HPLC? So as I mentioned, aqueous samples might be an area where HPLC might be the better choice over SFC, just because it has the ability to pull some of these higher compounds off of certain columns. So first we're going to look at vitamin B12, which is a water-soluble vitamin. And when we run that on the SFC, you can see that we do get the vitamin B12 to elute, but I will mention that this run was originally only supposed to last 12 minutes. So I then extended the run at 70% of my co-solvent, which in this case happened to be methanol. This was on a silica column. So when I extended that run, that's when we started to see this vitamin B12 elute. And you can see the peak shape isn't great. And if you look on the left-hand side of this chromatogram, you can see that our absorbance is actually quite low. And I injected 0.5 ml of vitamin B12 onto the column. Of course, that was dissolved in water. We used a gradient going from 5% methanol in our supercritical CO2 up to our 70% co-solvent. This total run length was 17 minutes, which is actually pretty long for an SFC separation. So now what happens when we use an HPLC? Well, with the HPLC, as I mentioned before, we have the ability to do reverse phase. So we can use a C18 column. So that's exactly what we did here. We used a water methanol solvent system going from 10% methanol all the way up to 100%, and we see a really nice peak coming out about 8 minutes. You can see how sharp that peak is. That's our vitamin B12, and really this total run length was close to a half an hour, but we could have stopped this run at 10 minutes. So really, when we compare this HPLC injection compared to the SFC, we were actually able to cut down the runtime with the HPLC here, looking at that vitamin B12. Now, there's other things we can do with the SFC as well, and that's we could try a different stationary phase. So here we tried a different stationary phase. This is a PEI column, and we again injected 0.5 ml of our vitamin B12 onto this column, and you can see our runtime is now shorter. It's comparable to what we saw with the HPLC, still eluting at 70% methanol, and our peak shape isn't great, but it does improve. So here's an example where we see the HPLC outperforming the SFC, and you might not have some of these specialized columns, these PEI columns laying around if you're using an SFC. Well, if you have an HPLC, you're definitely going to have a C18 column around. You're going to have these different normal phase, reverse phase columns if you're using an HPLC. So let's look at another aqueous sample. Let's look at ATP, and let's run that again on the SFC. Well, again, we're going to use just silica column, methanol as our co-solvent, and you can see here we actually flatline, and we are not able to pull this ATP off of the silica column with the SFC due to the polarity. It's just too polar. It sticks to the silica. We're not able to increase the polarity of our solvent system enough to where we're able to pull that ATP off the column. Now we can try to use a percent of water in our methanol, in our co-solvent, to try to increase the polarity of that system. And when we do that, we run a 95% methanol, 5% water as our co-solvent. we might be able to see some sort of peaks start to emerge on this chromatogram. But again, the absorbance is so low, I don't really know if you can call these any sort of peaks. I still don't think we're pulling the ATP off of that column. It's just not polar enough. But if we run that with the HPLC, again, we can use a silica column, but we can run that in a Hillock type fashion. So our A solvent is actually going to be acetonitrile with 0.1% TFA, and our B solvent will be water with that 0.1% TFA, a gradient from 5 to 50% B over a course of about 15 minutes or 55 column volumes. And you can see here, we do get that ATP off of the column at around 35 CV. We do see some tailing, but it's a lot better than what we saw with the SFC. The other thing that we see is maybe some impurities eluting early on before that 10 column volume mark. And we can also look at the UV absorbance of our peak. You can see that red line at that 35 CV mark, and that's our UV spectrum. Down at the bottom, we'll get a nice peak at 260, identifying that as ATP. Another area where we might want to use HPLC over SFC is when we have some similar achiral compounds that we need to separate. So for this example, we're going to look at caffeine and theophylline, and they're really quite similar in structure. Caffeine's going to have a methyl group connected to a nitrogen, where theophylline will just have the hydrogen connected to that nitrogen, and that's circled on your screen there. So what happens when we load these two samples onto an SFC system with a silica column? Well, we get a really nice, beautiful peak. The only problem is we're supposed to see two peaks. I loaded both caffeine and theophylline onto this silica column, and we're only getting one peak with methanol as our co-solvent. Again, using a gradient from 5 to 70% of our co-solvent. So there, we're not able to distinguish between these two compounds. But the nice thing with HPLC, again, is we're able to use a C18 column, we're able to use reverse phase, and the SFC, we're not able to use reverse phase quite yet. So here we're going to do a gradient of going from 10 to ultimately 100% of our co-solvent. I ended this run at 15 minutes, but that gradient was going to continue all the way up to 100% of our B solvent. But you can see with the HPLC running that in reverse phase, we're actually able to distinguish between these two compounds, but we're also able to get baseline resolution between caffeine and theophylline, and that's going to allow us to have really good fraction purity. And that's exactly what we would like to see when we're trying to separate two different compounds. Now, SFC, you could use another type of column instead of the silica column to try to improve that separation. So if we use a PEI column, you can see how much better our separation is compared to the SFC with our silica column. We're getting really good baseline resolution, even better baseline resolution than what we saw with the HPLC. Same sort of gradient, going 5 to 70% methanol. The only problem with this is, what if you don't have a PEI column laying around? I mentioned this before. If you're an HPLC user, you're most likely going to have a C18 column, be able to use reverse phase. With a SFC, are you going to have a specialized column laying around in order to complete this separation? So we just went over when HPLC might be favorable over SFC. So now let's review what else we talked about today. We started off talking about what supercritical fluid chromatography is. And in order to answer that question, we had to ask another question, which was, what is a supercritical fluid? So if you remember, we went over that phase diagram and how supercritical fluid doesn't have those definitive boundaries or that definitive phase change going from a gas or a liquid into that supercritical fluid. We also talked about modifiers or co-solvents and how the addition of these modifiers affect the critical point of our supercritical CO2. We then went over the tail of the tape of HPLC and SFC, comparing the two, which really highlighted the pros of SFC as it is a greener and faster chemistry. You're able to achieve higher linear velocities with SFC. You're going to cut down on the amount of organic solvent you have to use with SFC. Your run times are going to be faster. Your energy consumption is going to be lower. But we also talked about HPLC and its versatility, how you're able to perform reverse phase with HPLC, and that's going to open up the door for a lot more stationary phases with HPLC. We also talked about how HPLC is tried and true. It's going to be one of those chromatography techniques that people are comfortable with and are going to come to time and time again. We then looked at a TSO chiral separation, looking at those pilot injections on both the SFC and the HPLC. We compared those head on. We saw that we would save a lot of time and solvent with that first initial chiral separation. Then we looked at running stacked injections on the SFC and compared that to 10 injections set up in a queue on the HPLC. And that's really where we started to see that solvent and time saving capability of the SFC thanks to the supercritical fluid and the ability to run stacked injections. We then looked at running a theoretical stacked injection on the HPLC, which is a possibility to perform on an HPLC system if you keep that run isocratically. And we still saw that the SFC was able to save you some time and some solvent due to that supercritical fluid. And then we just went over when to use the HPLC over the SFC. We looked at some aqueous samples, some samples that are extremely polar. And remember that the polarity limits of the SFC have yet to be defined. People keep releasing new literature out there where they are able to elute some high polarity compounds off of the SFC. But with the results we saw from our aqueous sample work, we saw that the HPLC, thanks to being able to run reverse phase or use a Hillock type separation method, we were able to get better results with the HPLC. We then looked at some difficult to separate achiral compounds. If you remember just a little bit ago, we showed the SFC wasn't able to separate between those two compounds. We saw one nice peak, and then when we ran reverse phase on the HPLC, we started to see those two peaks. Same with running the SFC with a specialized column. We were able to get those two peaks with really good baseline resolution. But are you going to have those specialized columns laying around your lab? Maybe not. With HPLC, you're most likely going to have your silica for normal phase. You're going to have some sort of reverse phase column, whether that's a C18, a C8, a C4. Majority of the time, those columns are going to be around. So that brings us to the question of why we're all here today. HPLC or SFC? Which one should you guys choose? And really, that's going to come down to what are the needs of your laboratory. Both HPLC and SFC are great separation techniques, each with its own pros and cons. So which one should you choose? Well, like I said, that's going to depend on the analytical needs of your laboratory and what are your applications. Are you looking to cut cost and time? Well, then SFC may be the way to go. Are you looking at chiral separations? Well, again, SFC may be favorable looking at those chiral separations. Do you struggle to get your sample into solution with HPLC solvents? Well, supercritical fluid might help get that sample into solution. Or are you looking at a wide range of compounds? Well, HPLC's versatility might actually help with that. Or are you looking at aqueous samples? Well, then reverse phase HPLC might be the best way to separate that. So there's not an exact answer to that question. And I know probably some of you were tuning in to this webinar to get an exact answer for that question. Should I use HPLC or should I use SFC? And that's going to just vary from lab to lab. It's going to depend a lot on what your analytical needs of your laboratory are. So either way, whatever you decide to use, whether it's HPLC or SFC, Teledyne ISCO offers two great AccuPrep systems, the AccuPrep SFC and the AccuPrep HP150. Both systems are capable of accomplishing all of your separation needs.
With that, I would like to open up the floor to any questions you guys may have. So there is a Q&A button on the bottom of your screen. If you guys want to type in your questions in that box there, we can start answering a few of the questions that you guys will have.
Okay, perfect. Got a couple questions coming in here. First of which being is, what about natural products and plant extracts? And that's been growing in popularity over the recent years. So what about those natural products, plant extracts? Would you use SFC, HPLC? And normally that would be an HPLC purification. But as of recently, there's been a couple new developments, a couple pieces of literature out there that we've seen where nearly all major natural product classes have been able to be purified with SFC, actually. So that's all your phenolic compounds, alkaloids, lipids, all of those have been able to been purified with SFC. And as developments continue to be made with SFC, that's going to release new stationary phases for SFC that could separate those lipids, those alkaloids, even better than what we currently have. And it's just going to increase the capabilities of the SFC. And if you're working with natural products, you might even be surprised with what type of retention you get with just a silica column. Again, you're starting with that really non-polar supercritical CO2, so you might be surprised with what type of retention you get. We've seen varying levels of retention with different natural products. So that's something to keep in mind too. And when you're working with this SFC as well, you have to remember that you're working with that supercritical CO2, so that's going to really decrease the amount of solvent you have in your fractions. A lot of people, when you're working with those plant extracts, those natural products, you're going to be collecting and you're going to be fractionation or putting your sample into fractions. And with HPLC, you're going to have a lot of solvent within those fractions. So the SFC is also able to give your rotovap a little bit of a break during those purification processes. Another question we have is, what co-solvents can we use with the SFC? And we talked primarily just about methanol, and that's going to be your most common co-solvent when working with SFC. But you can also use a couple other different co-solvents. You could use ethanol, IPA, acetonitrile. Any of those will do fine. Of course, ethanol, IPA is going to be in the same selectivity class as methanol. So acetonitrile might give you a different selectivity than what we had seen with methanol. And also, don't forget, if you're working with really polar compounds and SFC, don't forget about the addition of water to your co-solvent. And that brings up another question of, like, how much water should I use with my co-solvent? And a thing to remember when you're adding water to your co-solvent is water is going to have a limited solubility within supercritical CO2. So it's at 0.003 grams per cubic decimeter. So that's something to keep in mind. I've seen some studies where they got up to 15% water in their co-solvent, but with the column they were using, they didn't see an increase in efficiency when they went up from 10% water to 15%. So that's something to keep in mind as well. It doesn't mean if you add more water that your efficiency of your SFC separations is going to increase. And again, if you're working with a hydrophilic type column, that's going to increase your efficiency just because you're increasing the polarity of your solvent system. So again, that's something to keep in mind if you're looking at doing or adding water to your solvent systems. We have a couple questions also coming in. Let me give these a read. One is, I also got this morning with the earlier airing of this webinar. We're talking about running reverse phase with SFC. And the question I got earlier this morning was, can you run a reverse phase column with SFC? And traditionally, the answer to that question is going to be no, because SFC is a normal phase type separation, but that doesn't mean that you can't run a C18 with your SFC systems. If you're looking at some of those nonpolar compounds, you actually might be surprised with the retention you get with that C18. Now, just remember, when you're working with SFC, that A solvent's going to be your supercritical CO2. So that's going to be your non-polar solvent in that case. Now, normally in reverse phase, you're going to be starting from polar going to non-polar. And since SFC is this normal phase type separation method, you're going to go from non-polar to polar. So that's something to keep in mind if you want to throw some of your reverse phase columns onto your SFC. Another question is, can we run the SFC system with more than one compressed gas at a time? So you'd be looking at running supercritical CO2 or another supercritical gas. And with our AccuPrep SFC, currently we just have that one compressible gas, which is going to be your supercritical CO2. You've probably looking at trying to change your solvent systems is where this question is looking at, trying to change that selectivity of that supercritical gas or liquid that we're sending through the system. And currently with our systems, we're just stuck with that supercritical CO2. Another question is, where can we get some of these PEI columns from? And right now, I believe from Teledyne, we offer a 2EP column, we offer a dial column. I'm trying to think of our other prep columns that we offer. Of course, we're going to offer that silica column as well. I would have to check and get back to you about the PEI column. I'm not sure if we're currently offering that, so I will check on that and I will get back to you on that question.